Welcome everyone. We'll begin straight away, but just a quick housekeeping note. If for some reason we lose our internet connection, please stay with us. We'll be right back. Or if you lose your internet connection, please just log right back on. So as we talk about handling media and buffer powders, we look at what problems are we solving when we try to choose the right solution. Really, it's pretty straightforward. We want to reduce the powder handling processes so we can always reduce labor, increase efficiency during the handling process. As Paolo mentioned, we're always considering minimizing dust exposure, and that's a safety issue for operators, and also it reduces cleaning risks for having dust in the environment. Automation is always a key, so we look at how can we automate the transfer of bag handling, again, eliminating safety risks, and we'll see an example of how we want to protect operators from carrying heavy powder transfer bags in the process. And really, we want to provide a solution to deliver powder into a hydration tank, effectively eliminating the clumping and floating powders to enhance the mixing process. We know that's a problem, that different powders will act differently. And so if we can have a solution to enhance that delivery, we can make that process more efficient. And finally, always looking to reduce the amount of consumables such as cleaning wipes, extra tools, auxiliary pieces, and so forth. We're always looking to enhance the life cycle sustainability when using the single-use products that we'll show. So why are there different solutions? And we'll show three different types of solutions. Well, every plant is different and every process has its own idiosyncrasies. So we have tank sizes are different. The elevations certainly for those tanks are different. Sometimes we have to climb a mezzanine. Sometimes it's closer to the ground level, but certainly tanks and elevations are a big part of the reason to choose one solution over another. The recipes and the volumes of powder that's being handled are different. So each biologic has a different need for the amount of powder to be added. Powders, again, have different characteristics for the flow, how they can flow from a transfer system. And then we have the clumping issue as well. And we'll take a look at that solution to help reduce that as an issue. Powders will have the different mixing characteristics. And so, again, we're looking for ways to improve the mixing profile during the solution. And finally, we recognize the biopharmaceutical market continues to migrate from durable stainless steel technology to single-use systems. And so we will focus 2 of the 3 solutions on single-use products. So what can be implemented for better powder handling? The 3 solutions we'll take a look at today include the 2-ported 3D powder bag, the EZ BioPac. Again, we recognize that drums are still used for loading powders into tanks, whether that be drum dumping or scooping. So we'll take a look at a unique product, the cone liner. And lastly, a durable solution to really automate the process, assist with some mixing capability in looking at the JETMIXER, which is a 1-step powder into liquid system that can be placed in a controlled area to automate the system. So looking closely at the 2-ported 3D EZ BioPac, we see the example of sort of the common 1-port 2-dimensional powder bag on the left. We have our 2-ported 3D powder bag, the EZ BioPac example on the right. So you can see, again, what we're trying to solve here, mainly in the filling process of the powder bag, is to streamline that process for the operator. So on the 2D powder bag, usually that has a smaller tri-clamp connection, or that one single opening. So that's the 1 port, that one single opening where the powder is filled into and eventually will be discharged from. And to make the filling at least somewhat reasonable, often a funnel is used to make a bigger target to fill into. Where on the 2-ported 3D EZ BioPac, this 3-dimensional circular construction allows for a very large target for filling very quickly, really making that process as quick as possible and as accurate as possible. Jumping into that a little bit further, here we see, again, another example of the EZ BioPac. And recognizing that often the dispensing is done in a laminar flow hood or other somewhat controlled area. But the key here is the large open target for quickly filling the EZ BioPac. Here the operator is scooping from a pail. This could be pouring the pail into the EZ BioPac or scooping from a drum. But again, moving very quickly to do that fill because the operator doesn't have to worry about weight adjustment because of the wide open top. That weight can be adjusted by scooping powder out if they do a little bit of overfilling. So you also see we have no extra funnel or extra tools and so forth. There's no filling frame that is an external support. So very, very streamlined. So again, the whole process is meant to create a fast and easy filling process that's also accurate. You see on the picture on the right, we've added a dimension of a 40-inch working height, and this can be key, particularly when dealing with some type of laminar flow hood or some kind of fume hood area that the filling might be done in. Here we're showing a 25-liter EZ BioPac, and the ergonomic working height, including some room for the operator to lift above the EZ BioPac and do the filling. We see it's about 40 inches. So there is some height there, but it is an ergonomic height, and the motion for the operator is fairly good. And we don't need an extremely large laminar flow booth to do that. When we look at a 2D powder transfer bag in the same size, a 25-liter, recognizing that the volume per inch of height on a two-dimensional powder transfer bag is going to be a lot less. So we need more height. So here we see we've gone all the way up to 57.5 inches as the estimate for the ergonomic motion. So the operator has to reach much higher. The laminar flow cabinet has to be much larger, or the entire workspace has to be larger. So this can be problematic when doing a powder fill, and then also realizing the operator will have to fill into a smaller target, have to be more attentive to accuracy, because as you can see in the picture at the bottom, if the powder bag is overfilled, if the target is missed and the weight needs to be adjusted, that can be a challenge to do. Another tool is needed, a scoop to reach down into the powder bag to scoop some powder out. So this is very important. One other aspect of using a two-dimensional powder bag when doing the powder fill is the tri-clamp. The clamp that closes the powder bag from flow. So in the example on the right, the red clip, that's put in place after the operator does the fill. You'll see on the 3D EZ BioPac that end where the tri-clamp is at is sealed by the factory. So the operator doesn't have to worry about doing the clamp correctly and risk powder bypassing and again contaminating the area. We're always trying to eliminate extra parts that cause more work and extra parts. Also, there's a continued risk that this may get into the process. So, the key word here is eliminate. So the EZ BioPac has the option for a non-gasket design with the tri-clamp. See in the picture on the right where the operator is connecting the powder transfer bag, there is the common gasket that is at the connection point. Well, the tri-clamp was designed for liquid applications, and so the gasket is critical in those applications. With a powder transfer, this really isn't necessary to have the separate gasket, and what has been done on the EZ BioPac is to mold that gasket into the tri-clamp flange, which still gives us that very nice powder seal. This reduces the time to make the connection because we don't have that extra part that we have to position and then bring the powder bag into place. So we certainly save that, and we also reduce the risk that gasket is loose. It could get into the process. It could fall on the floor. There's many bad things that can happen with the gasket. So going with a non-gasket seal is a really important idea. So here's that connection again. So what we're trying to do also is offer a full range of connections for different nozzles that exist on tanks. Often with powder transfer bags, a 2 or 3 inch, maybe a 4-inch connection with a tri-clamp is available. If the tank may have a 6-inch tri-clamp connection available, this is very good, helps for powder flow when we have a much larger nozzle to really get the charge done quickly and effectively. But if the powder bag only has a smaller tri-clamp connection, then a transition piece will be needed. Again, one more piece that's required, needs to be cleaned. All of these things, we're trying to reduce those amount of extra parts. So the EZ BioPac is available in a full range of tri-clamp connection size from 1.5 inch to 8 inch in the standard tri-clamp, and then 2 in the DN series, the 100 DN and the 150 DN. Another thing we look at when dealing with powder transfer bags is hang up and retention in the transfer. So really, again, looking at that 2-dimensional bag, we've noticed that there is quite an opportunity for powder to remain in the bag after the discharge. Now, certainly the operator can take advantage of the flexible and shake the bag after discharge, but we still find that many customers have added this rinse nozzle that we can see on the 2D bag. And this is because there are hang-up areas in the pinch seam welds that hold the bag together, or part of the construction of the bag, and also a lip or a hold-up point at the tri-clamp weld where the tri-clamp is welded to the plastic film of the powder transfer bags. And so this is really an extra step when we have to wash that bag out to remove that residual material, to be able to take the time to connect, let's say, a WFI line to the rinse nozzle, do the rinse, and then disconnect that. So extra work for the operator, slowing the process down. Really, we're trying to avoid these kind of things. And you'll see the picture on the left, the EZ BioPac is shaped quite differently with the 3-dimensional design. Everything is circular, there's no hang-up points. We'll talk later about the welding type. It's not the pinch seam, which has the opportunity for material to hang up. And the key thing is a study done for the EZ BioPac to show that after complete discharge, the typical or average powder retention is 0.06% of the original content. So a very small amount of hang up that we have to deal with when using the EZ BioPac. So we want to add up these advantages and look at, well, what does that mean in terms of time savings and labor savings and production time? So the things we've looked at so far save time in powder dispensing, and that's a big aspect of this. So actually, when we're doing the powder dispensing, how can we save time? We want less retention when discharging. Again, if we can avoid using a rinse nozzle, if we can get complete discharge, this is a very good thing. Always reducing the risk of contamination. The industry, the biopharm industry, is becoming more and more stringent on particulate. And the last thing we want to do is have powder bags and transfer mechanisms that actually put particulate into the environment that we have to deal with more cleaning, more validation, and so forth. So we really focus on reduced risk of contamination and reducing those extra components and reducing the cleaning materials that are needed for extra components and wipe downs and so forth. So getting rid of the gasket, getting rid of the funnel, things like that, we definitely want to eliminate. And so you'll see we have a study that went through the entire process that'll show a 60% time savings when using a 3D EZ BioPac versus the 2-dimensional single-ported bag. So in this study, we went through the whole process. There's more detail behind the study, but I think it's pretty compelling when we look at the numbers. So the study was done using a 25-liter bag, both the EZ BioPac and the single-port 2D. We studied a quantity of 50, so saying the batch of the powder transfer was for 50 bags. And so really the compelling time saver was at that dispensing process where we've circled in red. So you see here that using the EZ BioPac, we've reduced the time by more than half, much more than half, when using the EZ BioPac and that large opening, not having to manage the clip to close it and the risk of of potentially having powder come out and so forth. So dramatic savings there. And then when we take a look at the whole process through bringing to the powder transfer room, lifting, connecting, and discharging. So we have a total savings of about 60% in this study. So it's really an interesting product when we look at the three-dimensional bag and how that really saves a dramatic amount of time. Now, this study didn't include using the rinse line on the 2D bag, and so in those processes where a rinse line is used, the savings is even going to be more dramatic, really more compelling. So again, one of the aspects we're always looking at is operator safety, and we know in many powder transfer applications, the powder bags are being manually carried in the facility, and a lot of times up steps to a mezzanine or some area where the operator can access the nozzle to make the charge. And so we obviously really want to avoid steps anytime we can. We really do want to avoid operators, having to have the burden of carrying a bag of powder, if you will. We know that limits typically are at about 10 kilo for any operator to carry, but we really want to get away from this. So we look at two automation mechanisms. One's has to deal with transfer carts and lift systems. So again, we want to take these bags out of the operator's hands and automate that through a mechanical mechanism. And then we'll go on to a second part where Dave Howes will speak about the JETMIXER powder delivery system that's going to further simplify and improve that powder charging and take the burden off the operator from having to do manual transfers. So we've seen a very interesting lift system that can be used with the powder charge bags and with the 3D EZ BioPac. And so this example is from Mito Systems. And this is a lift system that can allow multiple bags to be lifted from the floor level up to the charge nozzle, swung into place, as you can see in the diagram on the right. It pivots into position. And it also has a trolley on it. So again, we can have multiple bags. Once everything is lifted to the position, a bag can work around the trolley to the nozzle position, be connected and discharged. Once it's discharged, the trolley can take the empty bag away and now bring the next bag to charge into the tank. So this is very, very efficient. It takes us away from the operator having to climb the steps and so forth each time with a bag. Just the operator will be positioned there only to make that connection. So loading occurs at the floor level. That's a safety advantage and so forth. The design takes any size bag up to 100 kilos. So if they're less than 10 kilo, they can go on the one part of the trolley. If they're more than 10 kilo, oftentimes they're on a halo that's designed to pick up a heavier bag. We also know that drum charging is still done on somewhat of a regular basis for powders in the biopharmaceutical area. And so the common mechanism that we see is the drum inverter. So we see in the picture on the right that a drum has been loaded onto a cone in a drum lifter and an inverter. The cone and the drum are picked up and inverted over where the charge needs to be. Now here we're showing a kitting operation where multiple drums are being charged into a large 3D powder transfer bag, another range of the ILC Dover company called the Dover pack. But there can be bulk kitting where multiple medias can be added, or multiple buffers could be added into one larger bag, or just the fact that perhaps 5 or 6 drums of the same powder can be loaded into that large bulk bag. And the advantage being is we're not transferring all of these drums to the process area. We're not having to lift multiple drums to the tank to do the charging. And so by using one large powder bag, we can make that one transfer. But with that, we have the product contact area of the stainless steel cone, and that often comes with a butterfly valve. And so what we've developed is the cone liner, which follows the contour of the cone, is in position so that now the stainless steel cone becomes a non-product contact area, and we reduce the cleaning and the need for cleaning of that stainless steel cone. And we also can eliminate the butterfly valve in some cases using a fold or a wire tie system. We can have a dust tight closure, so as the drum is lifted and inverted, that it is there's no powder leakage until that fold or the wire ties, as I said, are opened and allow the powder to release. So again, by using the cone liner, we reduce the amount of cleaning, we reduce the amount of dust discharged into the environment. We certainly create a closed transfer, again, further reducing contamination. So here, I'm going to hand it off to Dave Howells, who's going to take us through another transfer mechanism called the JETMIXER. Dave, take it away.
Thank you, Scott. The fundamental challenge we are discussing here is how to get an ever-increasing volume of powder into a tank and then mixing it to complete hydration. The representation here is admittedly very simplified, and many of you will be involved in a manufacturing facility with a hydration system looking more like this. Such systems come in different scales, but have many common features such as stainless steel tanks and pipework. The complexity of the latter resulting from not just the need for moving process materials, but delivering and removing CIP and SIP fluids. And this installation is typically within a clean room space, which immediately limits the type of equipment and devices that can be moved into it and used. So just what are the challenges? Increasing demand for products means more and larger batches. Basically, more and more powder is being handled. And powder handling is challenging, far more so than fluids. In addition, typical weight restrictions on powder bags results in an increasing number of bags that must be filled and moved to the powder charge point on the tank. This schematic captures another common challenge. The nozzle itself is not in a convenient to get to location, particularly when carrying multiple powder bags to that position for charging. I have personally seen fire lines of operators handling bags of powder to each other across a floor and up a stairway. And the charging operation ergonomics are further challenged by the frequent scenario where the real estate on the tank head is limited. Put another way, there is no room to move. This means the acts of removing a nozzle cover, positioning and attaching a full powder bag with a gasket and clamp are all done by the operator, having limited room to maneuver and stand comfortably. We have all heard of injuries and powder spillages occurring. So, the statement seems obvious, but Scott previously mentioned many of the powder bags used today are liquid bags, poorly adapted to the purpose of powder. The success of our own EZ BioPac bag has been it is powder bag designed for this purpose by powder bag experts. Pedigree matters. So looking at this operation, this powder handling operation can be made immediately easier by bring the powder charge point down to the crowded top of the tank and complete it on the floor of the hydration area. This is not only eliminates the transportation of the powder bags to the top of the tank, but allows the operation to be undertaken in an open, clear, great area, greatly improving the overall ergonomics. So what technologies can be used to charge the powder from this remote point and get it into the mix tank? The first established technology is pneumatic transfer, that being where gas is used as a transport fluid. This very simple schematic provides a representation of dense phase transfer, one of the two prime methods of pneumatic transfer, and the one most applicable to this application. The discussion of pneumatic powder transfer using dense or dilute phase is a webinar series in itself, but let me just summarize here that dense phase transfer has a proven capability to move a vast range of powder types, and thus more suitable to this application, where one tank will be charged with dozens of different powders with great variance in their physical properties. It also has the benefit of being able to have a number of arrangements to charge the powder into the transfer system from a range of different bulk containers, from bags to drums of all sizes. However, there are some disadvantages of dense phase transfer in this application. The first is the limitations in achieving precise charge weights because of powder holdup in the entire transfer system. The methods required to achieve high powder recovery, complicating the system and the subsequent cleaning of it. Fine dosing arrangements are available, but these are typically not successful when one system is used for multiple powders. The second drawback of dense phase powder transfer is the space needed on top of the mix tank for the chamber required for the gas powder separation. We've already detailed the challenge of real estate on many mixed tanks, and a significant amount of space is required for the pneumatic transfer equipment. Finally, this method of powder charging does nothing to improve the actual mixing of the powder with the liquid, as these two parts of the mix do not come together until they are inside the mix tank, unlike the following methods. The ROTOR device has been historically popular in the bio sector and uses the liquid within the mix tank as a transportation method. In summary, a ROTOR device is driven by a motor, its rotation acting as a pump to recirculate the liquid from the mix tank and generate a vacuum at the powder charge point, shown again here as a funnel, although in this instance, this is frequently the powder entry method. However, the increasing volume of powders now being processed have exposed the weaknesses of this device, the most significant being the noise from the large motor, limitation on ability to move certain powder types, the need for regular cleaning because of blockage, and a design that does not facilitate easy cleaning, it having a moving part at the heart of the system, so some disassembly is required. This device does not allow easy introduction of liquid, a regular requirement for buffers, and it does generate a high volume of air intake, creating foaming issues and pH instability. Like the ROTOR device, the JETMIXER uses the liquid from the tank as the motive force to operate, the heart of the system being an ejector through which liquid is pumped, thus generating a vacuum which is used to pull in a powder. However, this device has many advantages over the ROTOR device, the prime ones including A, no moving parts, thus reducing power consumption and maintenance. B, easy to clean in place. C, can process the broadest range of powders with great variation in physical properties. D, allows the addition of liquid, an off-required application. The simplicity and effectiveness of this product means other possibilities can be realized. Add a second pump with whatever pressure head requirement you need, and the return leg to the mix tank can be almost any distance you wish. Imagine locating your powder addition operation away from your crowded hydration room, or having an area dedicated to powder handling with all the best applicable technology laid out in the optimum ergonomic fashion. I think the benefits are obvious, particularly considering the ever-increasing amount of powder handling operations that are being undertaken. Should also be noted that, as with many previously mentioned pneumatic transfer solutions, a host of methods are available to deliver the powder to the jet mixer charge point. The method determined by the bulk container, bag type, and even containment level. And I purposely say containment level, noting that this requirement is not typical for the types of powders handled in the biosector. However, ILC has thousands of installations in the traditional API synthesis and OSD processing arena that provides high containment, that being the prevention of powder particles leaving the processing volume and thus protecting both operators and environment. Equally, this also prevents particles entering the processing volume, thus maintaining cleanliness, quality, and enhancing the GMP capability of the powder handling operation. The benefits are great when you can engage a powder handling company to solve your powder handling problem. Scott, back over to you.
Well, thanks, Dave. That was very interesting to look at those different options and the advantages of the JETMIXER. Again, I think a point that Dave brought up that's very compelling is treating the powder process as a powder process and not borrowing technology from liquid handling. Powder handling has different challenges than liquid processing, and so the solutions have to be considered in a way to meet those different challenges. In powder handling, we have a lot of stress that can go onto a powder transfer bag because of the lifting and positioning. Failure is not an option. We cannot have a powder bag with media or buffer being lifted into place and have a weld seam fail or some kind of flaw that is going to release powder. So in this case, we need a very high tensile strength of the film because it's critical that we do not fail on moving that powder. And then we use a design of a 3D bag, which really distributes that load. Very interesting in how the design allows for the materials to yield a much higher strength when lifting the bag. And then unique welding processes like a lap seam weld to assure that the weld area becomes the strongest part of the powder bag. You can see here a single-use EZ BioPac that can go up to 140 liters and a 100 kilogram load and still maintain a 2.5 times safety factor. So we look at these materials for the strength as well as the actual work that's being done. And so when we're using a high strength material and a design that allows to move larger amounts of powder, we can make a larger powder transfer bag. And here we show a full range from the smaller EZ BioPacs up to the 180 liter size. So again, the EZ BioPac size range is based on leveraging the strength of the material of a unique linear low density polyethylene film called ArmorFlex. So again, looking at this, as always in the biopharm industry, the validation of the product contact material is critical in all stages. Certainly when liquid handling is being done, there is very in-depth extractable leachable studies, very stringent extractable leachable studies. And that's also can be the case in the powder area and looking at the materials of contact. Following the BPOG extractable and leachable outlined protocol, looking at the guidance that we get from ISPE and the single-use technology handbook, we really look to see how do we choose the right material. But again, when we're handling powders, this is a different situation than handling liquids. So one of the unique things in powder handling is the potential of a static charge buildup and a release. Very common anytime powder is being handled that the powder flowing against a film wall, a plastic wall, can create a static charge and be released, which can be a safety problem for operators handling these and so forth. So here we're showing the structure of the ArmorFlex 114 film, which is a monolayer structure. And within that monolayer structure, we've put an anti-static additive. The key thing here is the anti-static additive still has to go through and pass these stringent extractable and leachable tests to be sure that we're not putting anything into the process that shouldn't be there. So we look at qualifying the material for a powder handling bag, and as always with most product contact materials, we're looking at regulatory qualifications and physical properties. And so the list of regulatory qualifications is quite extensive. This is all of the regulatory guidance or regulatory requirements that ArmorFlex 114 film passes that's used for the EZ BioPac. But as much as the regulatory qualifications, then again, we have to be sure that we have the physical properties as well. So you can see we have very high tear strength, high tensile strength, very strong elongation at breakpoint. And then lastly, we have the unique part of the powder transfer bags is to meet the required static dissipative directives that are out there, the Chilworth incentivity, and for Europe, the ATEX directive in meeting the surface resistivity required for the ATEX directive. And then when it comes to the material, it's not just the material, but then it's also the manufacturing environment that the powder transfer bags would be made in. So the EZ BioPac is manufactured in an ISO 7 certified clean room. All of the operators that work in the clean room go through CGMP training. And in fact, there's annual retraining for CGMP requirements in the manufacturing area. The facility does meet the ISO 11137 protocol, or the VD Max protocol, which that leads us into controlling bioburden. We also obviously control particulate in the room. And then using the VD Max protocol with the ArmorFlex, the EZ BioPac is ready for gamma radiation. And again, here we look at gamma radiation as a key aspect of the biopharm industry. And so we have special packaging when products will be gamma radiated to assure that the sterility that's achieved is maintained. So there's a double packaging that is done for all products that are gamma radiated. So a quick case study just to look at how a two-port 3D EZ BioPac can be implemented. So we have some photos that are fairly clear, but taken in the plant setting to take us through that case study and really what the changes were to take an existing process using stainless steel bins and change that into using a single-use 3D bag. So here in step one, we see the stainless steel bins were being used. You can sort of see in the front of it is the lifting mechanism. So the bin is filled and put into place, connected to a tank, and then discharged. So the first step was to modify the bins so that we remove the top of the bins. So the picture in the middle is showing the operator being able to load like an EZ BioPac with a large open target area in top, so we can have a very quick and accurate filling. So the top of the bins were opened up, and then also the bottom. So we can see on the picture on the far right, there was a tri-clamp on the end of the bins. So we just opened that up, and that allowed for the neck of the EZ BioPac to come through. And now we've got a single-use product that's protecting the bin and really becoming the product contact material. And it's looking just like an EZ BioPac. But the case study goes on, and we go into step three, where we really want to eliminate those stainless steel bins. And so a lightweight filling frame was developed. And so again, we can see now we're getting into a true three-dimensional two-ported EZ BioPac in a simple to use filling frame. We see the operator filling again into that large target. And if you notice, the EZ BioPac folds around the stainless steel frame, protecting that so that the frame, if there is some spillage, is not a product contact, and it's protected with each EZ BioPac that's docked and filled. And lastly, in step four, we have the EZ BioPac in use, where it's brought to where the charge will be and connected to the vessel and discharged. So what was accomplished here? Well, in this case study, there was an expansion going on, and so to keep up with the expansion, then additional stainless steel bins would be needed. So that becomes a CapEx problem. It becomes not only buying the bins, but buying the, putting on the cleaning technology for the bins. So really wanted to eliminate the stainless steel bins and eliminate the cleaning that goes with this. Going with a lightweight filling frame, much easier to handle, much easier for the operators to work with, and it takes up less floor space. The filling time was reduced when we go with the two-port open design. We have that large target. So the production was expanded without expensive CapEx for the bins and the washing machines. And again, we reduced the risk of contamination by using the single-use powder bag. Anytime we know in the biofarm space that we can use a single-use product and go away from cleaning, then we have a benefit of the risk of contamination is reduced. So in summary, taking a look at our presentation today, we see that biofarm powder handling is not the same in all facility, and so there need to be options that are available to meet the demands of each facility. The two-ported 3D bag are purpose designed built for powder handling. The 2D single-ported bags seem to be a migration from liquid handling into powder handling, but here we have the 3D two-ported bag as really for these media and buffer applications. Applying lifting systems and transfer carts, it can improve the operator manual operations and improve efficiency and safety. As Dave presented, the powder into liquid systems can be very interesting, and focusing on the JETMIXER, it solves several problems simultaneously of how to get powder into the process. As always, with anything that's a product contact material, the material of construction and qualifications, the overall performance has to be evaluated when implementing a solution. And again, the powder process is different than the liquid process. So some of the requirements like the anti-static material are good to evaluate to be sure that the right materials are being chosen. So we're looking at the business case for using the right solution, whether it's in a new facility or in the case study and upgrade in an existing facility for better performance and to reduce the labor needed in the powder handling process.